Okay, room is full, doors closed. Let's start a little bit earlier. Welcome everybody to this presentation, Java 4.11. We can say 12. Kotlin, code coverage, the best friend bytecode. My name is Evgeny Mandrikov. I work at a great company, SonarSource. You might know such a product as SonarCube. By the way, who knows, who uses? I hope you do. I hope you like them. But this company can only dream that they own my opinion. That's my usual disclaimer. And we are not going to talk about this company. We are going to talk about something different. We are going to talk about Java code coverage and such a great library as Jacoco. By the way, who knows, who uses? Okay, some. And about Eclipse Ecolemma, which is a plugin based on Jacoco. I'm co-lead on those two projects. I work on them in my spare time for about 8 years already, a little bit more. I work also on some other open source projects, but that's not the point. And before we start, by the way, another check. Is there guys who work on Java compiler, like from OpenJDK? No? Okay, so I can speak freely. Is there guys from JetBrains who work on Kotlin, on IntelliJ? No? Okay, I also can speak freely. Let's go ahead. So during work on these projects, we are testing 7.5 JDKs. Now already something like 8.5 because we also test early access builds. Why we do this, we are going to see a little bit shorter. Out of all this testing, we of course sometimes find the bugs. But I would say that we find the bugs not in our product, but in JDK. This happens. And of course, okay, sometimes we develop new features. For example, code coverage report of Jacoco version 0.8.1 for some Kotlin classes was looking like this. After some new features we implemented, without any changes in any tests, it started looking like this. Why this happened, what those features are, this is exactly going to be this talk about. Before we start, it's important to understand that Jacoco works only on class files. It receives all the information from class files. Source files, okay, they're shown to you at the very end, but in the process, they do not play any role. And we're going to see this. So this heavily simplifies things. Also complicates, but simplifies. Java agent, super simple integration. You don't need to rebuild your application to get code coverage working. You just attach Java agent. This opens door for us to cover some other languages than Java because, well, bytecode is the same, so this should work for Kotlin, theoretically. This should theoretically work for Scala, etc., etc. Why theoretically? Because we're going to see on which problems we face on the practice with such languages. Again, absence of source files is not an issue. So you can actually measure code coverage if you do not have source files at all. That's pretty cool. You get someone else's code and you can run some tests on it and see code coverage out of this. And of course, it helps us to cover some new syntactic sugar, which the ones that doesn't change class files, the ones that doesn't change bytecode. For example, switch expressions, it should be no-brainer for us to support because it's just a syntactic sugar over already existing bytecode. Okay, no row string literals were dropped from JDK 12. There is a little mistake on this slide, but it should be also no-brainer for us. And so on, so on, so on. And before we really start, here is a real disclaimer. Sorry for that, there will be a little bit of blood out of JVM. Sorry for that, there will be naked Java compilator, naked Kotlin compilator. Sorry for this, we're going to talk strong language. We're going to talk primary bytecode. Forget English, forget French, etc., etc. And sorry for this, I will try to do intense violence of your brain. If you're not sure that you're ready, you can still try to open door and exit. So let's check also to orient me a little bit. Who knows Kotlin? Who want to hear more about Kotlin than about Java? Okay. Half. Okay, we will try to do both. So, ready? Let's go. Java. Let's take, as a starter to warm you up, let's take a pretty simple example. Java empty class with the name bless me. Who agrees that this class is empty? It's empty, there is nothing inside. Who agree? I agree. Okay, let's make a check. Let's check. So serial version ID, empty. Some other opinions? Let's don't guess, let's check.
Default constructor.
Thank you very much. So how we're going to check? We compile it, then we're going to decompile it. For the decompilation, we're going to use Java P standard tool out of GDK, minus v verbose, minus p show me privates, etc., everything, on the resulting class file. What we're going to see inside is, okay, some metadata about this class file, information about which bytecode version we do have here. Reminder, 52 major version in bytecode is Java 8. We're going to see constant pool. This is first and the last time we're going to see constant pool because it's quite big. I'm going to strip it out from other slides. Constant pool is basically all the constants used in your class file. It's strings, it's method names, names of attributes, signatures of methods, etc. Why it is useful? Because, well, then if you have a lot of calls of the same method, you can simply reference the same constant pool entry. And here we see the actual content of the class. And, well, blessed place cannot remain empty. There is indeed constructor, default constructor in Java. We all know that it exists. Here it is. What's inside of this constructor? It's also not empty. It actually contains invocation of a superconstructor. We know that to construct any object in Java, we need to call the constructor of its parent. In this case, we also know that parent of every class is actually a Java-lang object. So here we call a constructor of Java-lang object. And nothing in Java can fall through the method, so we need to return from the method. Here's a return. And here is exactly the little connection with the source. Here is exactly why JCoco is capable of showing you something on the source. We have a so-called line number table. Line number table says, starting from the bytecode instruction 0, everything what follows was compiled from a line number 1. And that's exactly how JCoco can connect what was analyzed on the bytecode with the final report on the source code. And that's it. Well, we also have source file attribute, which says, okay, file name from which this was compiled is this one. This is the only piece of information which connects us back to the source code. Let's take a look on the other example. Again, pretty simple, also for warm-up. enum. This time, to be sure that it is empty, we called enum empty. And there is no constants in it. This compiles, so do we agree that it's empty? No, because it should contain, again, constructor, default constructor. Let's check. We compile it, we decompile it. What we see inside? Not at all a constructor. First thing which we see inside is some magical field values. We do not expect that, but okay, it's there. It is private, it's static, it's final. All those keywords we know, fine. It is synthetic. Remember this word? We're soon going to see what synthetic means. It also magically contains some methods which we didn't write. It contains method values, which returns empty. But we all know these methods. Actually, if we write our enum constant dot values, we are going to get all the values of enumeration. So we didn't write this method. Compiler generated this method for us. There is also method value of. Again, generated. We all know this method. It returns, by string representation of constant, it returns the actual constant. And yeah, here it is. Here is constructor that we expected. And well, there is also static initializer. This static initializer exactly initializes a field values to put all the values of a constant into this field so that method values could return this constant. Why this is all important for the tools that work with the bytecode, which analyze this bytecode? Because user didn't write this code, but the compiler generated this code. So if you analyze a user bytecode and start reporting something to the user, they're going to see something strange. They're going to see something what they do not expect. So for example, old version of JCoco was producing such a report saying, well, you didn't test it method value of, you didn't test it method values. Why we should test them? It's unclear. They're generated. Let's trust the compiler. We can in some cases. So we need to filter them out. We implement the filters. Report starts to look a little bit better. Unfortunately, in the first iteration, we didn't realize that some people indeed do not define constants in enums. They use enums as the containers for static methods. So in such enums, constructor is never called. So you also need to filter out constructor. We filter it out. Remember synthetic attribute. What this beast is, we can read in our Bible in the virtual machine specification that there is a synthetic attribute. This Bible simply says synthetic attribute marks everything what does not appear in the source code but appears in the bytecode. Except, of course, as in any language, there is some exceptions, except methods enum values, enum value of, and default constructor. Exactly the constructions that we've seen. Why this attribute was introduced? Well, a paragraph a little bit later explains this synthetic attribute was introduced to support nested classes and interfaces back in JDK 1.1. Let's have a check why. So, a little bit more complex example, nested classes. So what do we have here? We have an inner class. It's nested into the outer. Inner class has a private constructor. And we call this private constructor from the inner class. First question to you, will this compile? Of course it will, there is no problem. Java language allows all this, so we compile it, we decompile it. What we see inside? Again, to remind you, it's Java 8, major version 52. Here is our example, here is constructor invocation. If we look a little bit precise on this invocation, we will notice that actually invocation contains some magical argument with the value null. We didn't write this. Our constructor has no arguments, right? Why so? Let's have a check. To check, we need to have a look on the inner this time. And what we will see in inner, we will see our private constructor. And indeed, it has no arguments at all. There is no arguments. What we will also see that Java compiler generated another constructor on behalf of us. And this constructor accepts some argument. What we could notice is that indeed it's synthetic. This time it's synthetic, generated construction, marked with synthetic. What we could also notice is that our constructor was private. On the topmost left you see the private. This new constructor is not private. It's package local. Why so? Well, while Java language specification allows you to write such a code where classes within the same nested classes could access private constructions of each other, Java virtual machine doesn't allow this. For the Java virtual machine, it's two completely different classes. They are not at all nested. They lie next to each other, and you cannot call the privates from one to another. So to overcome this difficulty, to overcome this property, it was decided, okay, let's invent synthetic attribute. Let's generate such a constructor, which is package local, which can be called from the class. Package local synthetic. Invokes our private constructor, simple delegations, that's it. If this time we will look on this generated class, which is used as a null argument, we will see that this time it's indeed empty. This is an example of an empty class. Why is this class also generated? Because, well, another problem is that you can't have two constructors with the same signatures. So you need something to denote this second package local constructor. Yeah, and again, this class now synthetic. Thanks God, all this changed in Java 11. In Java 11, we got nestmates. We got nest-based access control, so all this crap which was introduced a long time ago could be reduced. If we will have a look on exactly the same source code, but this time compiled with Java 11 for the bytecode version 55, we will see that there is a loss in weight, there is no more constructor generated, we have only our private constructor, and that's basically it. Also, we see the new attribute, which is exactly was introduced to support nest-based access control, which says, well, I am nested in this nest host, which is class outer, which is pretty cool. Another example looks like this. We have an outer class, it has a private field. And we have an inner class, and in inner class we do an increment of outer class. Can you guess what is going to happen? Something should happen, because again, it's private. We're not supposed to access private members. Again, we're not going to guess, we're going to decompile all this, and we're going to see. Again, back to Java 8. In Java 8, what happens is we are looking exactly on the increment, but we do not see increment. We see magical method invocation. Access $00, not 7 for some reason, 8. What is this? We look on the outer. In the outer, indeed, there is new method generated. It is synthetic, package local, again, to overcome this problem of access to the privates. And here is the bytecode which does the increment. Again, for exactly the same reason, to access the private field, we need to invent such a tricks in Java. Again, all this changed with Java 11. With Java 11, we lost weight. We do not need to generate those accessors. We can directly increment the counter because there is another new attribute nest member, which basically says, well, I'm an outer for this list of classes. So as I'm an outer, I could access the privates, etc., etc. And yes, if you look on the inner, we will see that there is nest host again, which says, yes, I confirm that I'm an inner of this outer. Another interesting example, also related to synthetics, so-called bridge methods in Java. So what do we have here? We have two classes, A and B. B extends A. We have two methods. One is in A, another is in B. And the method is in B overrides the method in the A. So far, so good, I hope. The only problem is that the method in B decides to change signature. It decides that it will be returning not an object, but a string. This is perfectly valid, this is allowed. However, in the places where callers expect that they will be calling a method fun that returns object, we are supposed to have a method in B which returns an object. And to do so, different signatures, and to do so, again, Java decides to do a trick. Here is original method, and here is a method that callers would expect, the method that returns an object. Again, it's synthetic. It's also marked with an attribute bridge, a new one, and it simply delegates to our original method. Exactly to this time, not to align the private access, but to align expected signature. Out of all this, logically, what we could conclude is, well, for any bytecode analysis tool, we should simply ignore synthetic methods because they do not have any relation to the source code, right? User shouldn't see them. It's compiler-generated code. Maybe, maybe not. Let's see. If you have a look on example of lambdas that appeared in which version? Sure. 7 or 8? Okay, you'll figure out this at home. So what we have here, runable.run, simply we execute a runable interface method run. And we pass the lambda to the method that does this execution. So here is a lambda. Lambda is an argument. Let's notice that lambda is on the line 9, and lambda contains joker, right? Simple, right? Right or not? Right. We compile, we decompile, we look what happens. Method exec, nothing special. We do an invocation of a method. Nothing changed. Here is our invocation where we pass as an argument, we pass a lambda. Here is magic happens. Where is joker? There is not joker, right? There is no constant joker. Where is line 9? There is line 8, line 11, no line 9. 9 here is a bytecode instruction, return, not the line number. All this happened to move to a new private static void lambda $fun $0 method, which is synthetic, which is generated. Here is joker. So this is a mechanics behind lambdas. This is mechanics behind invoke dynamic instruction. Lambdas, they appear as synthetic methods in the class where lambdas were declared. So if our bytecode, and here's line number 9, by the way. So if our bytecode analysis tool, whatever it is, findbugs, handbugs, or Jacoco in this case, if they will be ignoring synthetic methods, they would miss lambdas. So for example, here, is this exactly what was happening in Jaco version 0.7.1. We are missing lambda. We don't know anything about lambdas exactly because we decided to ignore synthetic methods. We need to fix it, so we decide for our bytecode analysis out of nowhere that because it's not specified that lambda is implemented like this. It's implementation details of lambda. So out of nowhere, we decide, OK, well, we need to ignore synthetics except if the method name starts from the lambda $. That works. That works perfectly. Another example, switch and enum. So we have enum. This time it's not empty. It has two constants, false true. And we have a switch by this enum. So two constants, switch. We compile, we decompile. What we could see that there is a switch, right? No problem. 3 cases inside of our method. And no, we see something strange happening here. We see that just before the switch, we perform access to some magical class that we didn't write. And to the field switch map, $switch map, $, in this class. What this beast is, let's have a look again. We can decompile this class. We see that this is generated synthetic class. We could see that it indeed contains a synthetic field. And this synthetic field is initialized in initializer. How it is initialized? Well, we take a particular constant of our enum, and we put ordinal of this constant into this array. And we assign the value 1 to the value of the array. And we do the same with the second constant. Again, little connection with the source. We could notice that this generated class has a connection with the source file. It maps back. Let's scroll a little bit. It maps back to the line of the switch. So for each switch on the enum, Java compilator generates synthetic class. It does so because while enum might change, enum might be provided in third-party library. Maybe it's not your enum at all. Switch always should work no matter how enum was rearranged. If you change the order of constants so that ordinals change it. Or if you added a new constant, switch should continue to work. To do so, you need to do a mapping between the switch in the bytecode and the original state of the enum. And this generated class exactly provides such a mapping. Again, simple conclusion, we should ignore synthetic classes, this time without exceptions, because otherwise they will be showing to the user that unfortunately they have a line which is not covered. Filters. At this moment of time, you might start wondering, do I have something non-synthetic? Unfortunately, or for a good, I don't. But inside of Java compilators, there is a lot. Let's have a look. Assertions. Simple example. We have assertion on the Boolean parameter. Simple, right? What should happen if we start this and pass true? Everything should be OK. If we pass false, what should happen?
You shouldn't use assert at all.
OK, we shouldn't use at all. Good point. But OK. Let's have a look. What happens inside? Inside, again, just because we are using assertions, we got some synthetic. You might say, again, synthetic. No. Besides synthetic, we got far more generated code, which is not at all marked synthetic because there is no attributes for generated bytecode instructions. We got something strange, which is invocation of class.desired assertion status, and we are passing our class in it. Why you all might know that in Java you can enable and disable assertions, right? In order to not always, for each assertion, in order to not always ask, furthermore, you can enable or disable assertions not only for the whole JVM, you can do this on a per class basis. For certain classes you enable, for certain you disable. So this would mean that each time we execute assertion, we should go to the runtime and ask runtime, could you please tell me what's the current status for me? Should I should I execute assertion or not? This is not so performant. This is actually expensive operation. So Java again does the trick. In order to not go to the runtime, we should I'm so sorry. Okay. Shit. Oh no, we're still alive. Yes, so we simply ask runtime once during initialization, we cache the value that JVM knows, and then we simply, each time happens assertion, we check the cached value. If assertion is disabled, we shouldn't execute assertion. If assertion is enabled, then, well, we do the check of assertion and either we throw exception or not. Again, why this is a problem? Because user didn't write all those branches. User didn't write if statements. So users do not understand why assertion statement contains actually 4 branches. Well, to decide whether assertion is enabled or not, and to decide whether to throw exception or not. And in case of Jacoco, it's pretty tricky case because you can't actually test one of those 2 branches, because then you need to restart your JVM with assertions disabled or assertions enabled. It's a very tricky case. We still have an open issue. We do not know how to solve this properly from an end user point of view, but we will have a look on this later. Another interesting example, switch on a string. Switch on a string, we compile it, we decompile what we could see inside. Inside we could see for some reason 2 switches. We had 1, right? You're not sleeping. We had just 1 switch. Agree? What happens inside? Inside happens pretty interesting thing. Apparently, in order to realize string inside of a switch, it's very performant to actually reuse a string hash code, because with a high probability, if you just switch by hash code, you will already know which string it is, because likely all the strings, they might have different hash codes. That's it. And the second, but no, yes, sorry, no. We also sometimes get a hash collision. So we also need a little bit of logic to compare with the original string. And this is exactly what happened here. 2 strings, they have exactly the same hash code. So below we have a couple of string equals to decide exactly which one of the strings we got after string hash code. And only then we perfectly know which switch case was taken, either first one, either second one. Again, this is a little bit of a magic that bytecode analysis tools like code coverage or finbugs or handbugs need to deal with, because user wrote just a switch, just 3 cases. He didn't write how many? 2 ifs and 2 switches. So again, we need to write some ad hoc filter which tries to map back the bytecode which compiler generates, to map it back to the source code, to show to the user, yes, everything is okay, there is 3 cases. So let's have a look on another example, finally. So we have try finally, and we have a couple of method calls inside. Super simple, right? Let's have a look. After compilation, we again decompile. What we see inside, we see the 3 invocations of method nob, but we had only 2. You're not sleeping, right? Let's check. Yeah, let's check. 2 or 3? I see 3 knobs, but the third one is a method declaration. It doesn't count. So to simplify our life, let's introduce a marker. So let's have a string, try finally. We again compile, decompile. What changed? We can see there is indeed, here is 1 try inside, and 2 finally. We wrote 1, right? Why this happens? This happens because in JVM, in order to implement finally, we could use so-called only exception table. And exception table doesn't say execute this instruction always, no matter what happened. Exception table says if exception happened, then execute exception handler. And in order to implement finally, you need finally happens, we all know, finally happens when exception was and exception was not, right? Right. So in case of exception, we're going to catch it. We're going to execute exception handler. And this is exactly the second finally. It's a finally inside of exception handler. Here is exception handler. And on a normal pass without exception, we also should execute finally. So in order to use exception table to implement finally, we actually need to duplicate finally 2 times. That's the trick. And And again, this surprises the users, because users wrote finally only once. However, we need to do the deduplication. We need to realize that two blocks of code, they're actually the same thing. So again, we write filter, we merge everything back, and user is happy, believing that he has no duplications in his bytecode. A little bit of archaeology. This was a little bit differently in version Java 1.4. In Java 1.4, it was not a problem to implement finally without duplication, because there was GSR and thread constructions, Java subroutine and return from subroutine. Looks like I have a missing slide, but okay. Apparently, those constructions were deprecated because with such constructions, it's much harder to verify the bytecode for the compiler, and verification is important for security. So in favor of security, was decided to do a little bit of duplication. Let's have a look on the other example, and given the amount of time, unfortunately, I think we may be not going to see the Kotlin. Try with resources. So we have resource, it's closable, and we have try with resources. I'm not going to ask when it was introduced, because I know that you do not know in which versions what was introduced. So try with resources. If we decompile it, we see a lot of bytecode. You even don't see anything because it's too much. We can zoom a little bit. We could see 4 times close, close, close. Why? Because we know try with resources should close the resource. In order to do this, for sure close the resource, let's call close 4 times. No, of course no. If we look on the other Bible, the Java language specification says the meaning of a basic try with resource statements, blah, 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 and such a beast. If you look deeper in this beast, we will look a little bit later, you could logically, at this moment in time, ask a question, could you please prove it that this is equivalent to the try with resources? I could prove it. Let's have a look on fun one. Let's have a look. I have try with resources that you've just seen. I also have fun 2. Ah, shit. Fun 2 is exactly what you also seen. It's a big beast. If we now compile file fun1, decompile it, save result decompilation in file1.txt, if we do exactly the same with fun2, but save it in 2.txt, and we are gonna do diff between 2. Here's what we're gonna see. Something changed because we did 2 compilations, but then only 9 numbers changed. No bytecode was changed. Let's check that there is some bytecode. Indeed, there is some bytecode. There is a lot of bytecode. So this is a pure compilation of this is a pure equivalent of try with resources. So what happens here? There is try catch. There is also finally. In finally, we do all the closing. If resource was not open, we need to check that. If there was no exception, we need to check that. So there is some ifs appear. Then we need to close. If exception happened, then we need to attach one exception to the other. All of this happens in finally. And we remember that finally duplicated. So that's why exactly all of this duplicated multiple times. Fun fact, in case of exception, in the following case, we always initialize resource, so there is no point to check now. So there is dead code. Another dead code in case of exception. We know that exception happened. There is no need to check for now, etc., etc. So this was a little bit improved later in Java 11. They reduced duplications, etc., etc. All this means that again we need to write the filters, and we need to adapt the filters for the particular compiler version, etc., etc. Unfortunately, time went up, so I skip a lot of funny stuff about Kotlin. You might find this presentation on Jacoco site, so don't worry, you go home, you see the recording on YouTube about Kotlin, and everything will be okay. Conclusion. Unfortunately, source code is not bytecode. This is very important. This also means that what you wrote in the source code is not at all what is going to be executed, because what is going to be executed is not even bytecode. Unfortunately, what is going to be executed is a jittered bytecode. Even this is not true, because there is a branch prediction, etc., etc., etc. So be careful. What you write is not what is actually executed. But unfortunately, this means that bytecode-based tools, they only have to guess. All of this is implementation details. There is no magical way to map back the bytecode to the source code. It's an unsolvable task, as we've seen, because multiple bytecode, the same bytecode as we've seen with try with resources, it easily can be a result of compilation of two source codes. How we decide? We can only guess. In Jacoco in particular, we assume that no one writes such a crazy source code because it's big. So we assume that it's always try with resources. If someone will really write try with resources like Java language specification says, in the code coverage report, we will filter this out, assuming that this is try with resources. So please bear with us. We developers as tools, you developers as bytecode analyzers tools, we have to live with this. We should write filters. Now that you know all the internals of Jacoco filtering, please bear with us and don't scream when code coverage report shows you something that you do not expect. Please just decompile and see what actually shown to you. Thank you very much. That's it. If you have any questions, let's just go out and you ask all the questions.